Okay, so for the first 10-15 minutes, I'll be doing some basic stuff. Till then, those who are like a bit familiar with these can try these problems, buffer problems. So these were not good problems. And for this one, I would suggest that you should try this at your own risk, like this one. So I think you can take a SS or something. Yes, so let me begin now. So we'll be doing multiplicative functions here, and this is a very good topic in number theory. So first of all, let's define an arithmetic function. So any function whose domain is the set of natural numbers, basically it's n to something, it's called an arithmetic function. And you say an arithmetic function is multiplicative if for every coprime mn, you have that f of m into f of n is equal to f of mn. Okay, so this is just the definition of multiplicative function. Now, there's like five important functions that we'll be needing. We'll be needing phi of n, which is the number of divisors of n, tau of n, and two new functions which I'll be defining. This is called the Mobius function of n. So this is defined as something as follows. So Mobius of n is 0 if like n is not square free. N is not square free. Uh, Now, if n is square free, then we let Mobius of n to be minus 1 to the power of the number of prime divisor it has, number of prime divisors. So, for example, if you take a very random number, say 6, 7, so Mobius of 6, 7 would be like minus 1, and Mobius of, say, 6, 7 square, it would be 0, and like Mobius of 1, since it has no prime divisor, so I'll put minus 1 to the 0, it will be 1. So this is a Mobius function. And now we'll do, and the second function is Dirichlet delta function. So we just define this as like, it's 1 if n is 1, else it is 0. So, okay, since we are done with definitions, so now I would like to show you this amazing property. So do you see this immediately? Just wait. Do you see this? This is basically saying that like some of the Mobius function taken over the divisors of n is that reproduces the Dirichlet function. So this is just like pi inclusion exclusion principle. So you can try proving this in for 2 minutes.
Wait, can you show the definition of delta?
Okay, delta function is just like 1 at n equal 1 and 0 at n greater than 1. That's it. So this basically asks you to like this thing is 1 if n equal to 1 and 0 otherwise. So as a hint, you should try to focus a bit on prime factorization of n, I would say. Okay, does anyone see like why is this sufficient to prove only for square free n? Like it is sufficient to prove this for square free and it follows automatically for all n. Does anybody see this why?
Yes, because if n is not square free, then Mobius n is 0.
Yes, exactly. So if n is not square free, then all the devices like which are contain a prime square would just produce Mobius 0. So eventually we will just be computing the sum of divisors of p, q, dot, 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 rs. We'll be computing Mobius d sum over divisors of this, where this is like the distinct prime divisors of.
Also, Mobius is multiplicative, so you only need to prove it for prime powers.
Perfect,
So
perfect.
you only need to prove it for p, and for p it's trivial.
For p and p prime power, it is trivial, and you can observe that Mobius is multiplicative. So I'll leave it as an exercise. So since Mobius is multiplicative, you are basically done. Now, the second proof of this, which I wanted to convey, is using principle of exclusion inclusion. So I told you, right, it's just sufficient to prove this for square free n. So if n is square free, then let me just write it as product of distinct primes. So p1, p2, say pk, and like n is this basically. Now, to compute this, you can just see that this is movies of the sum of these divisors. So either you take k primes, so the divisors which have k prime factors, k prime factor divisors. So that would be, then you have the divisors which have k minus 1 prime factors. Then you will sum of the times mu. But then you will sum these all up to number of divisors which have just one prime factor times the mu of that, which is just 1. So if you observe, then this is just alternative plus minus because like first of all you have k prime divisors, then k minus prime divisors. So the parity just changes. And you can just use the fact that the number of odd subsets of this is equal to the number of even subsets of this, like both are equal to 2 to the k minus 1. So you are basically done because like you have equal positive and equal negative contribution. Is that clear? Hello? Did everyone get this?
Yes.
It's
Okay.
clear.
Yeah. Now we'll be doing another special function called phi of n. So you probably know like phi of n denotes the number of coprime numbers less than or equal to n. So you does anyone know what this could be? Could anyone guess it? What this should be like?
The wait, I forgot. It's called the phi function. Like
Yeah,
the
yeah. This is the phi function, but like, what's the sum of it over all divisors of n? Like, let's say if I denote this as fn, then can you give me an explicit formula for fn if you? Anyone? Uh, so well, it turns out that fn is actually just n. So this just basically reduces down to n. Now, this is like very cool thingy because it's good that it reduces down to n. Now try proving this. So the idea is basically you could look at these fractions n by 1, n by 2, or L by n. So there are n of these fractions, And now try to count these fractions in another way. Basically, like try to count these fractions in another way that would just give this sum. So that will just prove this counting in two ways. So this would be n only.
Isn't it sigma phi of D?
Yeah, 5 of t, sorry, my bad. Yes, you're correct.
And at that another place you wrote that Mobius N. It would be Mobius D, if I'm not wrong.
Where? Yeah, it's
Um,
Mobius t, sorry. Uh, so basically what you want to do is that you will express this in simplest form. So you will basically count the numbers 1 to n in two different ways. So first of all, obviously there are n numbers, that's trivial. Secondly, we'll count these numbers on the basis of their GC division. So let's say we take a number I from these and we want to look at GCD I comma n. So trivially this has to be a divisor of, this has to be a divisor of n, right? So let's call this G of I basically. So this has to be a divisor of n. So this can take a divisor of like number of divisors of n values. So this can be 1, this can be till n, where these are divisors of n. So these numbers, the number of these numbers are essentially solutions to GCD I comma n equal to dk, where d is a divisor of n. Let's say if this has fk solutions, then sum of fk is what is the number of those. And if you notice for a device, so if you want this to be d, GCD I comma n to be d, so it's equivalent to having GCD I by d comma n by d as 1. So I by t is basically coprime to n. And moreover, you will know that I is less than n, since that's like, what is this? So I by d is less than n by t. So the number of such numbers are just by definition phi of n by d. And since you sum it up over all d, you get this like summation of d divided n, phi of n by d. Do you see that why is this equal to summation d divided n phi of d? Do you see this? Like, why are these two equal?
Yeah.
Yeah. Hello? Anyone?
Yeah, we see.
Okay, so you see, right? Because like n by d, the set n by d over all devices is basically the set d over all devices. Like if d is a divisor, then n by d is also a divisor of n. So this basically just follows. So we counted this in two ways. One, it's trivial that these numbers are n, and second we prove that the number of numbers in this set is actually this. So since we counted the same thing in two ways, they have to be equal. So we get this. Cool. But now, as you see that for getting these type of identities, we need to use some like complicated combi ideas or like have to think it through. So we'll develop some nuclear bombs and machinery so that these types of things become just trivial. So for that, first of all, let me like introduce you to Dirichlet convolution. So Dirichlet convolution of two functions is defined as this. So it's basically an operation between two functions, and when you perform the operation to between two numbers, you'll get basically another function which is equal to this. So let me call it hn. H. So like this is how it's defined. And does anybody see that Dirichlet convolution is just commutative, like f cross g of h and is equal to g cross f of n. Like these both functions are basically the same. So does anyone see that why digital convolution must be commutative?
Yeah.
Why?
Just replace D with N by D.
Sure, just replace D with N by D. So we'll just do it since, like, again, the same idea. N by D are the number of divisors. N by D, like, are the set of divisors of D. So if D is the divisor, then N by D is the divisor, and vice versa. So we get this. Now, the main thing that why is this thing useful? Like, why are we even doing this digital convolution thingy? Uh, is because of a famous thingy called basically, we'll use the fact that digital convolution of two multiplicative functions is itself multiplicative. So that just basically provides a lot of stuff to us. And using this, we can just bombard things and just prove anything. This is like a very helpful idea. So we'll be proving first that Dirichlet convolution, say you have f cross g of mn for two coprime numbers mn, this is in fact equal to f f cross g of m times f cross g of n. So, and for this, the necessary precondition is that f and g are themselves multiplicative. So f cross g is, in fact, indeed multiplicative. Does anybody see why? Like, this can be helpful because, like, this can be helpful to generate a lot of functions. So for example, if I wanted to compute the general formula for digital convolution of, say, phi cross 1, uh, so I can just compute it for prime powers and then just multiply it down to get the, like, answer for the general n. So that's why very useful. Okay, can anybody answer that? Like, what should be, let's say f of n is a function, and what should be this thingy? What should be this function? Where this is the direct Dirichlet delta function. Like, does anybody see what's this? Look at this definition, so you'll just get that. And in case you forgot what's Dirichlet delta function, here's the definition of Dirichlet delta function as well.
What did you ask again?
Can you, like, tell me what would this function be like if I convolute f with Dirichlet delta function? What function would this result in?
F of n.
Yes, this function is indeed f of n. So basically, if you use Dirichlet convolution of anything with the function, it will just, like, return the function itself. So Dirichlet delta basically is like an identity of the operation
Wait, why?
convolution. Okay, why? Because, like, f cross g of n is like d divided on this. So if I replace this, you know that Dirichlet delta of n is 0 when n is greater than 1. So you basically ignore all the terms except the term when d will
Okay,
actually be
makes
equal to n.
sense.
So this will just
Correct.
come out to be f of n. So this delta function acts as an identity to the Dirichlet delta to the convolution operation. Now we proved two results before, right? We just proved this result. Wait, what has happened to this? Does anybody see that this result is just saying that phi cross 1 and is equal? Okay, wait, no, let me write it like this. Phi cross f of n is n, where f of n is equal to 1 for all n. Does anybody see this? Like, this is basically saying this thing.
Yeah.
Right, so this is basically saying this thing. Now, this is f of n equal to 1 is a very special function for some reason in this lecture. So we'll be just denoting this by 1 of n. So like 1 of n is just 1. Okay. So I'll be replacing f by 1. So it says that Dirichlet convolution of phi with 1 is n. And over there, we proved this thing as well. So this thing again basically says that Dirichlet convolution of Mobius function with the one function is indeed the direct delta function. Everyone sees this? Or anybody has any questions? Is everyone okay with this?
Someone is asking to do.
Okay, let me check the chat. Uh, yeah, like, could you tell what someone's saying? Like, I can't see it.
Someone is asking what's a multiplicative function.
Okay, multiplicative function. We just defined a function to be multiplicative if for all coprime mn we have f of n times f of m is equal to f of mn. So this is like if
Please
a function
repeat
that
what
is
you said.
hello, what?
Please repeat what you said, like those functions.
Yeah, so those functions such that like for all coprime m comma n, you understand what's coprime, right?
I mean the Mobius functions thing, which you said now.
So this
I
if a,
don't mean that.
you mean what then? You didn't get what is Mobius function.
No, no, no.
Then which one?
This.
You didn't get this
This.
one.
Yes, yes.
Okay. Did you get this thingy?
Yeah.
Like you got this. So okay. So would you like to just explicitly write what this thingy is? Like just expand this by using the definition of Dirichlet convolution. So we just define this as this. Okay. We define it as this. So just use this definition. So this is summation of d divides n Mobius of t into 1 of n by d. Right? This is just the definition. Is it clear till now?
Yeah.
Now we just defined the function 1 of x as just 1 for all x. So this is just 1. And we just prove this right now to be Dirichlet n. So there you go. So you just have that this thing is equal to this thing. Is that okay?
Yeah.
So basically, in general, like summation d divides n, fn is just Dirichlet convolution of f with 1. Okay, cool.
Excuse me. I also
Yes,
had another question.
yes, please.
I think you said something about the multiplicativity about like the Dirichlet convolution.
Yeah, I'll prove that in a moment. So yeah, that's the next thing I'm coming to.
Okay.
So what I'm saying that is that if you have two functions f and g, which both of them are multiplicative, then the function f cross g of n, the f convoluted with g of n, this function is also multiplicative. So we'll be proving that right now. Let me just paste the proof. I think I have it. Yeah. Mhm. Yeah, so So basically, this is a short proof of why digital convolution of two functions, multiplicative functions, would be multiplicative. So the major idea of this is that if you have two co-prime numbers m and n, and you have a divisor d that divides m, then d can be uniquely expressed as a product of d1 into d2, such that d1 and d1 divides m1 and d2 divides m. And these d1, d2 are unique and they exist. This is basically
You
a
are as
bijective map from divisors of m.
and you are assuming M and N are co-prime, right?
Yeah, m and n are coprime, definitely, because that's the multiple. So if basically if d of m is a set of the divisors of m and d of n is the divisors of n, then like d1, d2 multiplied to d, it's basically saying you are constructing a bijection between this Cartesian product of the set with d of mn. And of course, you need mn prime. Does anybody see what are explicitly d1 and d2? Like, can you just write them in terms of m and n? Does anybody see that? Okay, so let me answer.
What
So
did you ask again?
yeah, so I'm asking that if a divisor, say d of mn, where mn are co-prime numbers, it can be uniquely factored as d1 into d2, where d1 is a divisor of m and d2 is a divisor of n. So can you explicitly give me what is d1 in terms of m n and d2 in terms of n n? Like, can you explicitly get that? You can get that in terms of dm and n.
GCD of
Yeah,
D
GC.
comma M,
Perfect, perfect. And d2 is GCD of.
GCD of M comma GCD of N comma D.
Perfect. So this is just a bijection. I'll leave the detail like it's a bijection to the reader now. So after you do this, then it's just trivial because you basically then reduce it to this one, and then since f is multiplicative, and since d1 is the divisor of m and d2 is the divisor of n, and m and n were coprime, so d1 and d2 also have to be coprime since the divisors of the coprime numbers. So we can just split the product like this, like this. Now we get till here. Now it's just double summation of things, which can be expressed as product of one summation times the other. So we'll get this is eventually equal to this. And so like we are done. Now this is very powerful. This is indeed a very powerful statement because now this can be used to bomb very good problems as well. So for example, if I had to prove that let's say d of n, which denotes the number of divisors of n. So this is the number of divisors of n, and I have to prove that this is multiplicative. Does anybody see a one-liner using this, like Dirichlet convolution of two functions is multiplicative? Does anybody see a one-liner using this that proves that dn is multiplicative? So dn is multiplicative. Okay.
Isn't it just one convolution, man?
Yes, exactly. So it's trivial to see that 1 of n is 1, and this is obviously multiplicative function, which like 1 into 1 is just 1. So if you look carefully, d of n is just like one convolution, 1. And since 1 is multiplicative, so this has to be multiplicative. So this is indeed very just like trivial. This makes us trivial. Now, does anybody see we can immediately get tau of n, which is the sum of divisors of n, this time. Sum of
Since when is tau of n sum of divisors?
Like I'm just denoting it that way. I don't like
That
sigma.
is just wrong.
I think it's denoted sigma n or something. But okay. Like, let me denote sigma n for now. But it's okay. Like you can take any notation of n. Does anybody see again a one-liner to this? Like, why is this multiplicative?
Yeah.
Okay, so tell.
What did you ask?
Does anybody like, do you see the one-liner to this? Like, prove that this
Ye-
function is multiplicative.
Yeah.
Okay, so what's the one-liner?
One
What?
convolution identity.
Yes, exactly. So this is just one convolution identity function. So identity function is just like f of n is equal to n. And obviously identity and one are trivially multiplicative. So their Dirichlet convolution has to be multiplicative. And hooray, we're done. So this just bombards things. And that's this is really powerful. Now suppose using this, I had to get a formula for sigma n. So now that I know that maybe let me get a formula for dn rather. So using Dirichlet convolution, I have easily proven that d of n is multiplicative. So if I compute dfn for a prime power k, so this is just trivial k plus 1. Then indeed I have d of n in general because for any positive integers I can just take the trivial prime factorization of it. And then since it's multiplicative, so I'll just write it as d of p1 alpha 1 into d of p2 alpha 2 and so on till d of pk alpha k. So this just indeed just turns out to be like pi of k plus 1 alpha I plus 1. And therefore just have a formula for it in general. And this we can just get the general formula for phi of n, tau of n, d of n, and just like so much more. So that's why like, this thing is very useful in particular. So now let's do some problem. So okay, we have this IMSL 2004 and 2. It just has 3 parts. Can you write this function in terms of what do you say? Oh, Dirichlet convolution.
Sure, we can see the entire problem actually.
Yeah, exactly. So like this is just trivial as the Dirichlet convolution. So do you see how? Like the first part is at least like direct by Dirichlet convolution.
Sorry, I can't see the entire problem.
Oh, you can't see that. Okay, sure. Do you see it now?
Yes, thank you.
We can just like first do n minus phi n.
Uh,
Well,
what?
no, sorry. Like we can do phi n plus d divides n.
You're saying this?
Like I'm just saying no. I'm saying like we can rewrite this as phi n plus d divides n and do the same thing.
Okay, so you're writing this as pi of
Wait,
n.
no. What am I saying? Never mind.
Yeah, what it is. Okay, so it will be useful to rewrite the sum as like follows. So I divide then um uh f of I. And how do you define f of I? So f of I is basically the number of k less than n such that GCD k comma n is I. So basically hashtag k such that number of k which satisfy this is what you call f of I. And k is obviously less than equal to n. So
Wait,
we use
you're
this.
using F again, or is this different?
Yeah, this is different.
Then rename it.
What? Okay, rename it. All right. So, does anybody see that why this should be true?
Yeah, because the GCD always divides n, so it has to be a divisor.
Yes, exactly. So, do you see now how do we proceed? G of I, wait, G of I into I. Yeah. Multiplied by. So basically, you are just summing up the GCD of k equal 1 to n. So GCD can take like values from values of the form I, where I is a divisor of n. So for each I, it's counted G of I times, right? Because those many k's are there solutions to this. So each I is counted G of I times, and you just sum it up over all divisors of all I. So you'll get this.
Wait, what have you written?
Okay, so you get what is G of I,
Oh,
right?
okay, I times GF. Okay, no, yeah, got it.
So this is I times G of I. So this is I times G of I. And do you see what is G of I explicitly? Do you see what's G of I explicitly?
It is n divided by I.
No, phi of n divided by I. So like G of I is like the number of k which satisfies.
Right, I see.
So this condition would be equivalent to having GCD k by I, comma n by I equal to 1, right? Just divide by I both sides. And since k is less than equal to 1, k by I is less than equal to 1 by I. So essentially the number of such k by I is just phi of n by I. So it's just phi of n by I, right? Times, yeah, it's just I divided n. And you very well see this is in terms of differential convolution as well.
It's phi convolution identity.
No, it's not phi convolution identity. It's, let's say if you define another function h of n as phi of n times n, then it's h of n convoluted with the 1.
What?
Then like if you define h of n to be this phi of n
Why
times.
can't you just say phi convolution identity?
No, this is not phi convolution identity because like I mean it is phi convolution identity, but like it's not direct that it's phi convolution identity because like
It is direct, right?
no, this will first turn out to be h cross 1, right? Because like 1 of well.
No, like just directly in the
Okay,
convolution
right.
notation.
Right, you are right. Yes, coping. Yeah, so it's I times phi of n by I, so that's just phi convolution identity. So phi convolution of identity of n. And since identity is multiplicative, phi is multiplicative, convolution identity has to be multiplicative. So this is just basically done. Hooray. And the rest two parts are essentially building upon the same idea how we got the formula of d of n. So try to get phi cross identity of n explicitly in terms of n. Like you can do this for prime powers first and then just get it for general and using the prime factorization. And then you will get this. Like then you just equate it and it's one liner from there.
After we got that, like phi cross identity of n was equal to that. Like, how did we determine that it was multiplicative? Like,
Okay, you got it here, right?
yeah.
Wait, we proved something. We proved that like digital convolution of two multiplicative functions is multiplicative, right?
Yeah, yeah,
So do you see that 5 is multiplicative
yeah. Oh,
and
oh,
it is multiplicative?
yeah, I see.
So this has to be multiplicative.
Got it. Thank you.
So yeah. And similarly, like the rest two are left as homework, so you can do that on your own. Basically the idea is like we got the formula of d of n just using the fact that d of n is multiplicative. We first computed it for prime powers and then use the prime factorization of n to compute it in general. So similarly, compute phi cross identity of n first for prime powers, then compute it n in terms of prime factorization, and then you just set it equal to an to just get n in terms of a. So you'll just get that. And then you will just determine the third part as well. So that's just like a homework. Like the main idea is conveyed. Now let's move on to a bit harder problem. Do you know what's primitive roots of unity first? Hello?
Not exactly.
Oh, okay. So we'll define like the roots of this equation x to the n is equal to 1 as the roots of unity. And a root of this equation, let's say alpha, is called a primitive unit of unity if it is a root of this, like if it's a root of unity. And alpha to the I is like not equal to 1 for all I less than n. So basically n is the like the first time that alpha to the power something gets 1. So if that's the case, then you just say that alpha is an nth primitive root of unity. So all primitive roots of unity, let's say whatever these are, let's say if we denote let's say there are k primitive roots of unity for n. So, and we denote the primitive roots of unity as something like n1, n2, and dot nk. So these are just the primitive nth roots of unity. We just have to prove that the sum of these is indeed the Mobius function of n. So this has a bit of black magic technique involved. Is it clear that what's primitive unit, nth root of unity first?
Yeah.
Right. So this is a sort of black magic technique. So how are we going to do this? Is that we'll use a technique called Mobius inversion. So what is Mobius inversion? Basically, if we have a function f and we know the Dirichlet convolution of f with 1, it's known like it's g of n, then how do you get f back from this? So you will first convolute both sides with mu, and then you will use the fact that Dirichlet convolution is actually an associative operation. So you will just put brackets over here, and you know 1 cross mu is Dirichlet delta, and f cross Dirichlet delta is f only. So you'll just get that f is g of n cross mu. Right. Yeah. Is this clear? Like this technique of doing this is called Mobius inversion, and this also kills a lot of problems directly. Have you even seen this? Hello.
Yes.
Yes, we
So
see.
okay, interesting. Now we'll solve this one. So The idea is like a bit hard to think of, but once you have this motivation of Mobius inversion, it's just like not that hard. So if I denote the sum of primitive nth roots of unity as
Wait,
say
why are these the primitive roots?
no,
Like,
these are like these. I'm calling these the primitive roots. These are like not the
no,
general
like you
notation.
said the primitive roots are the ones which are not the root of anything before.
Yeah, perfect.
So why is the GCD condition the same?
No, no, ignore this. Just like ignore this. I'll cover this later. You'll just write this is sum of primitive nth root of unity.
Sure.
So if I denote the sum of primitive nth root of unity, then just prove this. So the idea is you'll try to prove that Mobius cross 1 is equal to f cross 1. Since Mobius function is a bit hard to deal with directly, you know that Mobius cross 1 is delta function. So if you could indeed prove that f cross 1 is also delta function, then you will get this. And then you can just use Mobius inversion and just basically convolute it with mu. And since this is delta, so you'll just get that f is equal to mu. And we're done. So indeed, it just suffices to prove that f convoluted with 1 is the
Wait,
delta.
but how do we know it's unique?
What unique?
Like
No, I'm
A
saying,
convoluted B equals C, then X
oh,
convoluted B equals C, then X equals A. Is that like true?
yeah, basically that's, no, it's not true in general, it's true for one, like one is special thingy. Because like,
Okay.
because you can, if you take one, then if you convolute both sides with mu,
Oh, okay. You can get back identity, so
you
it
can
is
get back.
injective. That
Yeah. So the thing is that Dirichlet operation is associative. So you can just put brackets on any two arbitrarily. And one cross mu, we just prove this is just like identity. Dirichlet delta. And you know that Dirichlet delta cross some function is just that function. So you'll just get this. And voila, you'll be done. So for this, you just need to prove this. So if I write this explicitly, f convoluted 1, this is summation of f of d over d divided n. Does anybody see this is just sum of nth roots of unity? This is just sum of nth roots of unity. Anybody see this? And you like, no, nth roots of unity are all the roots of this equation. So their sum will be like 1 if n is equal to 1, and otherwise like minus xn minus 1 coefficient upon xn, so it will be 0 if n is greater than 1, and we'll be done. It's basically the delta function only. So you just prove that this is just indeed
that
the,
is sum of nth roots, right? Not
yeah.
primitive. Like what?
No, f of d, like f of d is the sum of the primitive and primitive dth roots. Now you show that this summation is indeed the sum of nth roots.
Okay.
So that you'll just get that because sum of nth roots of this is indeed Dirichlet function of n, because like sum of roots is just minus coefficient of x and minus 1 upon x minus coefficient of xn.
Could you just repeat the last part?
Okay, so you got this one like this.
Yeah.
It suffices to prove this. So what you indeed do, if I write this f cross 1, just like expand this, so it's this, right? Right?
Yeah.
Huh?
Yeah.
So it's just this. So we want to prove that this is 1 when n is equal to 1 and 0 when n is greater than 1. Because that's the definition of a delta function.
Yeah.
But now if you observe, what is the sum of roots of this equation? Like x n minus 1 is equal to 0. So what will you get the sum of roots of this equation? Can anybody answer it? What's the sum of roots of this? What? Anyone there?
It will be 0.
Yep, it will be 0, but like there's a small case. So this will be 0 when n greater than 1, and in the case of n equal to 1, it's 1.
Oh, yeah, yeah.
So this is indeed the delta function. Right, that's how delta is defined. So if you could show that this is just sum of roots of unity, you are done. And you see how is the sum of roots of unity?
Yeah, it's the same thing.
Okay, so basically if alpha is a primitive root of unity, let's say, of x to the d equal to 1, it's a primitive root of unity of this, then it has to be a root of this equation as well, right? Since d divides n. You can just put to the power. If alpha is a primitive root of unity of this, then alpha is a root of unity, root of nth root of unity. Not primitive though, but okay. Right?
Yes.
Now, conversely, if x to the n is equal to 1 has a root, let's say alpha, then do you see that for some divisor d of n, for some d, I'm not saying for all d, for some d of n, alpha will be a primitive root of this. Like the first d to make this thing equal to 1 will divide n. Do you see this? This is basically order divides the thing. In n, do you say order divides?
Oh, what was that last part? Could you just say that again? That last. Yeah.
So what I'm saying is that any root of this x to the n equal to 1 alpha, say you have this alpha, then there exists a d which divides n
Oh, yeah.
such that x alpha to the d equal to 1, alpha to the d minus 1 equal to 0, and alpha is a primitive root of x to the d minus 1. So basically this is telling you that the first number to make alpha to the power something equal to 1, let's say if that is d, then d has to divide n. It's basically
Yes.
so this
Yeah.
is just basically, yeah, so this is basically order divides the thingy. Like, you know what is uh, order in NT, right? So this is exactly similar to that. So if D is the order of alpha such that it is equal to 1, then D has to divide anything which makes it 1. So D has to divide n. So since the order divides n, so just take D to be the order.
Bro, but where are you like doing the primitive roots? This is like all the roots, right?
No. I'll see this. I'll see that later.
Okay.
We'll do, see how we'll get to all roots later. But do you see that any primitive root of x to the d equal to 1 is indeed a root of this? And any root of this has to be a primitive root of x to the d minus 1 for some d. Right? Hello?
Yeah.
So do you see this? Like we showed two things. Any root of x to the d equal to primitive root of x to the d equal to 1 has to be a root of this, and any root of this has to be a primitive root of x to the d equal to 1 for some d divided.
Uh, sure, but aren't you counting multiple times then?
No. I'm not counting multiple times. I'm just making two statements. Are these two
Oh wait,
statements?
you'll count the primitive roots of D as well. Like you
Yeah.
won't count all the roots of D.
Yeah.
Okay, it makes
So
sense.
so these two statements are true, right? Like these statement 1 and statement 2 are true, right? Hello?
Yeah.
Yeah.
Yeah, even I have the same question. Like,
Ah.
we're taking the like when we looked at the roots, by Vieta's we had it that like it's 1 if n is equal to 1 and 0 if n is greater than 1. Like
Yeah.
that is the sum of all the roots, but like where are we like exactly including?
No, like we are not just forget about these things. One, I'm just making two statements in general. These two lemmas, can treat them as lemmas that will help in our main problem. Do you get these two lemmas?
Yeah, I get those two.
Yeah, so that's just fine. So do you see that like all divisor, so all roots of n are basically primitive root of x to the 3 minus 1 for some d, right?
Yeah.
Now, this function essentially just counts the primitive roots of x to the d minus 1 for all d. And we just proved using these two lemmas that that is indeed all the roots of x to the n minus 1. So this is indeed just the sum of all roots of x to the n minus 1, which is indeed tetra n, and so we are done. Did you all get this? Did you all get this?
Yes.
So that's why like Mobius inversion is kind of useful. And now we'll see like, okay, let's cook up some random function. So do you know that phi of n is like the number of coprime numbers to n, which is less than n, right? Now, can you give me something for sum of these numbers, like sum of all the coprime numbers to n, which is less than or equal to n, in terms of the function that we just studied? So, and let me tell you that if you just, let's say, suppose that function is fn, which is sum of all k, sum of all k, right? Such that this is true. So if you let this to be fn, can you get me an explicit formula for fn?
Wait, do you want just coprime or like with any GCD?
No, just coprime, just coprime.
Then like first of all, if D is coprime to n, then n minus D is also coprime. So we can try and pair them.
You can try and pair them. Perfect. So you can try and pair them and you'll get n times phi of n by 2. Right? Because like there are phi of n by 2 pairs you can form and each pair sum up to n. So you'll get this. And this is perfectly valid. But now let's look at a bit harder one. So now we just found the sum of all k. Now we want sum of squares of all k. Now this is a much harder one. Like how do you get sum of squares of all k? Pairing just won't work because k square plus n minus k square is just giving you nothing.
Oh wait, isn't it like kind of the same thing? Because like k squared plus n minus k the whole square is just what? N squared minus 2kn. So then you could repeat the same thing all over again, like as a summation of like 2kn for all k like coprime to n. And then you already know that as like the earlier f of n. So that's just n times phi of n by 2. And then you could get, I think, yeah, like
Yeah, so you're trying to use the previous result.
yeah.
Okay. Okay, that's okay. But the thing is that let's suppose I wanted to compute it for large powers. So suppose like I want to compute it for some power m in general, sum of all power m. So you won't be like just using the recurrence and doing the stuff, right? That would be just too calculative, right? So using the Mobius function, we get a solution to this. So if I denote f of m of n to be like sum of power of m of all cases that this is true, so we can indeed get this in terms
It's
of
like any power.
Yeah, it's any power now.
Damn.
So that is how like Mobius function helps. So I'll just write the answer once. Then you just see how is this true. Wait. Mu d divides m and wait, d to the power m. Do you see why is f of n equal to this? F of m. Wait, no, not I to the power. So do you see why it is equal to this?
Can you repeat what FM of n is?
F of m is the sum of mth power of all k which are coprime to n and which are less than equal to n. So indeed, this seems heavy.
Wait, how is this the same function?
Yeah, exactly. That's what I'm going to prove.
Oh,
So do you see that something called principle of inclusion exclusion? What just like this is sort of principle of inclusion exclusion because we are like Mobius will take 1 - 1 - 1 values, and that's indeed the idea to this. So if we try to use principle of inclusion exclusion, then we indeed need to consider first the prime factorization of n. So Fn is p1 to the alpha 1 times p to the alpha 2 times p k to the alpha k. So suppose this is the prime factorization of n, then what you could indeed write is f of m and as first of all you would like try to sum all the powers of m. Right, so like 1 to the m plus 2 to the m dot plus n to the m. Right. Then you subtract all those powers which are like divisible by p1. So you will have indeed the multiples of p1 which are less than n plus p2 to the m p1 to p1 to the m dot till p1 to the jf n by p1 to the m. Right. You'll subtract all the p1s because, and similarly you'll subtract all the pi's in general. But then you'd notice that you have double counted those multiples, which are multiples of p1, p2, p3, p4, and so on. So just I equal 1 till k. So indeed you would have to again introduce a summation. Say, yeah, the multiples of pi pj. So all the multiples of pi pj raised to the power m, right? So all the multiples of pi pj raised to the power m. So you would have to add those for all I comma j. Then you would have to subtract pi pj pk multiples, and then you'll be just doing so on. Do you notice how this translates to Mobius? So like over here, just one prime divisor was there, and you had a minus sign. Over here, you have two prime divisors and you have plus one sign. Over here, you have three prime divisors and you have a minus sign. So this is sort of what's Mobius function, right? Mobius of something is minus one if it has for a square free number if it has odd number of prime divisors and plus one if it's even number, right? So this thing basically translates to this summation. Now, what about the divisors? These are all the divisors which are of the form like product of primes, and these are divisors of n. Now, what about those divisors which are not product of primes? So, for example, if D was like not of the form some pi, pj, pk, pi, it is like pi square, p1 to p1 cubes. Then, well, in that case, you just have Mobius of that is zero, and so it just does nothing. So basically, ultimately, this just translates to this sum, and this sum is f of m by n by principal of inclusion exclusion. So you get this. And there is a nice simplification of this as well. You can simplify and like simplify it further, and you'll get a nice thing in terms of mn. So that thing is just left as a proof to the reader. So this is basically like why Mobius function is indeed quite powerful. You can't imagine to solve this without using the Mobius function. Like there is no idea you can get. So that is how. Anyone wants to ask any question?
Can you summarize the idea of this once more?
Okay, sure. So the idea of this was principle of inclusion exclusion. So what do you want? You want to sum of all powers m of the coprime numbers, right? So you first
Yeah.
sum power m for all numbers. So till n to the m. Then you subtract those powers which are divisible by like those number ms powers which are divisible by either p1, p2, pk. So you do that. So you're essentially subtracting the multiples power of p1, p2, or till p1 times this. And this you are doing for all primes, right?
Okay.
But the problem is now you have double counted the multiples of pi, double subtract the multiples which are both of pi, pj. So you'll add them again. And then you have then again double counted stuff like pi, pj, pk. So you will subtract them and you'll do that so on. And if you notice, this minus plus alternates and it depends on the number of primes. This is nothing but mu of the number of primes. Like if you just wanted to replace minus by a plus sign, then you can just add mu of pi, pj there. And you can add a mu of pi there. Right? Is this clear? Till there? Hello?
Yes, it is clear.
So you can add till this. Now, this is basically summation of what I have written. Okay, so I'll just write mu of 1 here as well. This is because like these are just the multiples of 1. So if I just write this term thing explicitly, then for a divisor of n, does that d is square free because like all the divisors are of the form pi, pj, pk. So d is square free. This is basically that. And then mu of d times the sum of the mth power of the multiples of d which are less than n. So multiples of d which are less than n are just like d, 2d, and sort of like till d times j of n by d. And you raise this to the power m, which is very interesting. Now, what happens if I just replace this, just remove this d is the square free condition? Does this affect me in any way? Like, does this affect me in any way if I just sum it up over all divisors instead of just square free divisors? Does this affect me in any way?
No.
No.
No, right?
Yeah, Mobius is 0 then.
Yeah, movies is 0 for all non-square free divisors, so you can just dump this condition off. And voila. You just got a formula for f of mn. And simplification is left to the reader. Like, you can simplify this a bit. So that is why movies is indeed a powerful idea. So I think we have few minutes left for the class. So we have 3 hard problems here. This is
Wait,
USD.
how can we
Yeah, sure.
how can we simplify that thing?
Okay, how can we simplify that thing? Like, that is left to the reader. Like, I don't quite know how to simplify. You will have to do some calculation stuff. Like, basically the idea of this class was to get till here because itself is very good. Now,
All
simply,
right.
so you can simplify that later. Like, we don't care about that. So now we have 3 very good problems. So obviously we can do only one of them today. So this is just USA TST P5, USA TST P5. This is Turkey and MOP3. And this is like, I don't want to reveal the source and I can't do this literally. I have not done this yet. So this is for those who like want to try a really hard problem. Okay, so just tell me between these two, which problem do you like more? Which one should I do? Hello. Yeah, and by the way, the idea of this f of m, and like I just got this f of m in terms of this. This is also like used in this question. Like this question is direct with f of mn that we just derived here. So indeed, this question is like a bit stronger version of this. So you can just take a screenshot and just nuke this question with f of mn that we just got. Okay. USA Motor 2025 P1. And so, like, which one of the two problems do you want to do now?
It's 25p4, right?
Oh, yes. Sorry. Before. Never mind.
Shall we do the China TST?
Actually, this is the China TST, but this is a bit out of my, like, I can't do this basically. This is 2024 P3 and this is known to be one of the hardest problem that has ever appeared on China TST. So I'm not that old enough to like actually do this. So like this is for the ones who just want to try a very hard problem and cope. So which one of these would you like to do?
The USA TST.
Okay, USA TST, is everyone okay with that?
Yeah.
Okay, so you have this. You just have a sequence n which is defined by recurrence. Now the idea is to basically every time you have some recurrence, this is defined in terms of GIF, like n by thing.
Mm,
I can't really see the problem. Could you move
You
the?
do show
Yeah,
the
this
full
is the
problem.
problem. This is the problem. Do you see this?
Yeah.
Can you
Thank
like
Yeah.
copy paste it to some blank space?
Okay, sure.
Everything's crowded.
Sure. Let me just do that. So this is problem. So there's a pretty standard and good idea. Like every time you have some recurrence in which like you have these n by 2 n by 3 all appearing consecutively, like all appearing together at once, you always just try to look difference at consecutive elements of the sequence. So what you would like to do is that you would really like to look at this an minus 1 because this is very useful in such problems. So this is summation a times f of n by I.
What is the motivation for already looking at this instead of doing other stuff?
Okay, what is the motivation? So the motivation of this is f of n by I minus f of n minus 1 by I thingy. This thing is just like very cool. Do you see this is 0 if
Okay.
I does not divide n and 1 if I divide n.
Okay, that makes sense.
So what we'll essentially just get is that sum of something which are just divisors of n, and then we can use much of the Mobius and digital convolution stuff that we have already done.
Okay.
And like that's basically the motivation of this. So I just wait. So this is I equal to 10. So indeed this is just sum of AD d divided n, and d is greater than 1 because we are not starting the sum actually from I equal 1, we are starting from I equal 2. So d has to be greater than 1 because of this.
No, it's,
So
wait, you can just write d is equal to 1.
d greater than 1, right?
No, like the plus 1 at the end, right?
Yeah, you can
Oh,
you can add 1 at you can
wait,
add
no, never mind.
yeah, we'll adjust for that in a moment. So okay, this is not AD, wait, this is BD because like you have AD minus 1, so that is BD. So does everyone get this? Basically, this was the major idea of the idea hashtag 1, basically major idea of this one. Everyone gets this.
What is the B here?
Okay, we have defined Bn to be the difference of consecutive elements.
Oh yeah, sorry.
So do you get this basically? BD. This like n by I and n minus 1 by I will be just equal if I does not divide n. So in that case, this will just be 0. And if in case I will divide n, so this will turn out to be a form of n by d minus n by d minus 1, and n by d is just d because like n by d is a divisor of.
Okay.
So this just turns to be this, right? So now, but there is a problem. Indeed, there is a problem.
Wait, it should be b n by d, right?
Okay, it doesn't matter actually. B of n by d. So then you will just like
No, but then the d greater than 1 conditions
then
then
no
should not.
then that condition will translate to d less than n actually.
Okay, yeah, exactly.
So like it doesn't matter since n by d is just a set of d. So yeah, you have this. But the problem is that since you want to use some sort of digital convolution, you hate this d greater than 1. Like this is very annoying. So you will like no, it's actually d less than n. My bad. What am I doing? Yeah, this is d less than n here. This is d less than n. My bad.
And b1 is 0 or something else.
What?
b1 is 0,
Well,
right?
b1 is not defined, right?
No, but it's part of the sum. We need to like define it. I think 0 is sensible.
No. B1 is like just not defined. Like we just define this for greater than equal to 2.
Sure.
So the thing is that you just hate this d less than n. Like you do not want this to interrupt your thingy. So I'll just make this sum this and I'll just add an extra bn over there. So I'll just get a 2bn. But
No,
so
but this sum has b1, right? How
yeah,
are
this sum
you?
has b1. We just add b. No. Actually, this was less than n condition.
I'm confused.
Okay, let me just clarify. So, I, huh. So you got that B of n is equal to this. Do you get this?
Yeah.
So, like, we just wanted sum to be over all d divided n. You don't want this extra d less than n.
Yeah.
So you will just add a bn to both sides and you're done.
Okay, but what about d equals 1?
So d equals 1 is just there already in the sum, right? Like d equal n is not there, d equal 1 is there. That's the problem, right? D equal n is the one that's causing the problem, not d equal
Sure.
1.
Continue.
Sure, then you just have this. But do you see a problem in this relation? Like, this relation breaks down at a particular value of n. Can you just spot that value of n?
It's equal to 1.
Yep. So when n is equal to 1, obviously this is not true. Right? Because 2b1 is not equal to 1. Since b1 is just like not defined. So now what we have to do is that we actually have to define b1 in some sense, because without that we can't actually continue, because then like, b1 is just not defined. So the most good definition of b1 would be just like a1, right? So I'll just define a0 to be 0 and you have b1 is equal to a1 equal to 1.
I think b1 equals 0 is more sensible.
No. This is actually more sensible because like we'll see in a moment why.
But wouldn't that like be wrong?
No. Why would that be wrong? Like you can just take
Because a n by n and a n plus 1 by n plus 1. Like,
no. Like what we have defined bn to be this, right? Now,
yeah.
according to this definition, this just defines it for n greater than equal to 1. So
Okay.
it depends on us what you want to choose a naught. Like you just can choose a naught independent of this recurrence. You don't care.
All right.
So I'll choose a naught equal to 0 and to get b1 equal to 1. So I'll get b1 equal to 1. Now this has a problem. So this relation is true for all n greater than 1, but at n equal 1, you have to add a little 1 as well to over this, right? Is that clear? So you indeed just add another function, that's the delta of n over here. So this is just 1 at n equal to 1, and for n greater than 1 is 0. And so we have just adjusted this in general. Right.
Right.
Now we'll use our famous Dirichlet convolution. So let me denote bn as now like I'm denoting as a b of n, just for some notation reasons. So you will get that 2b of n, and this is Dirichlet convolution of b with 1 of n, and this is delta of n. Now what we'll do is that we'll use Morris inversion now.
Wait, how do you know b is multiplicative?
Yeah, I'm not saying b is multiplicative. It could be
But
non-multiplicative.
you've done a convolution with it.
Yeah, I can do a convolution with it. I'm not claiming that this convolution is multiplicative.
Ah, okay.
Like this convolution could be non-multiplicative function as well.
All right.
Can you just explain how did the 2 come up there? Shouldn't it be just b of n is
Okay,
sigma?
the two came because like in the original summation, you had the extra condition that d is less than n, right? Because I was starting from 2, so you will apparently never get an minus 1, which is b of n, since I start from 2. So, but you don't want d less than n. So you just added a bn both sides to make bn plus bn 2bn, and this just becomes d divides n bd.
Wait, d less than n, how does it create a problem? Like d obviously divides n, so
No, d is less than equal to n, right? I mean, I just wanted to make the summation over all d less than equal to n. Like earlier, this was just summation over all d less than n. But
oh
to
yeah.
just feel this is a better
Yeah.
way, I'll just make this summation d less than equal to n. Make
Okay,
sense? Does that make sense?
Yeah, it does.
Okay, so you have this relation now, which is very interesting. Now, what we will do, you will just take the convolute both functions with both sides with Mobius function. So you will get modulus of n, and you'll get b of n back over here because 1 cross mu will become delta and b cross delta will become 1, and you'll get plus delta n cross v2. What am I writing? Wait, let me check. I have not made a mistake, right?
You've done delta of n instead of delta of d. Or is that intended?
No, that okay. Let me just do this thingy again. It seems to have a confusion. So b of n is equal to from this thing here, right? Since I equal to till n, so n has to be obviously greater than 2, right? So for all n greater than equal to 2, you have this bd and d is less than n. So you apparently just add a bn to both sides to just get this. This is for all n greater than equal to 2. But there is something that n equal 1 just does not accept this, and we unfortunately have to add a 1 for that. So for n equal to 1, uh, I'll actually have to add a 1. So to adjust for all n in general, I'll just add a delta n to this relation. So this will automatically become 1 when n is equal to 1, and this will be 0 when n is equal to 2, right?
So it's delta d.
No, delta n, right? D, you're summing
Like,
up it over t. D is not a fixed thing.
no, but you want to add only 1.
Yeah. Okay. No, it's something
Like,
like summation is this.
add,
Do you get it? No.
yeah, 2bn equals that plus 1. So where are you
Yeah.
adding the delta?
Okay. So I'm just generalizing. This is for n greater than equal to 2. Okay. This is for n greater than equal to 1. Now I just want to get a general relation for n greater than equal to 1. So I'm just using this. This just holds in general for n greater than equal to 1.
Okay,
Sure.
sure.
Now what to do? Yeah. Now we'll be using the digital convolution, Mobius inversion, I mean. So we'll be using Mobius inversion. So after like just convoluting both sides with Mobius, you'll get this. And then you'll get B of n is equal to 2b times mu n minus Dirichlet with Mobius of n. What?
Dirichlet into Mobius is Mobius.
Yeah, it's Mobius, exactly, since it's the identity. So if I take this to this side, I'll just get B of n is equal to this. Okay, now this is cool. Now this is as far as multiplicative function takes you to the problem. Like this is just indeed the like most important step of the problem, because without this, like there is no solution apparently known, or apparently I've seen. So now obviously you have to use NT. Like this is as like multiplicative function can take only this much power. So now you have to actually use NT. So see the condition that you want to prove. An is congruent to n mod 2000, 2 to the power 2010. So, so if the idea is like if you could find some consecutive ans, let's say AI plus 1, total AK, where k is very, very large. K is like very, 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 very large. So if k is very, very large, then and all these are the same mod to the power 2010, then one of these has to be the same mod, their index mod 2010, right? Because like one of I plus 1 or till k has to be like, let's say this the common value of mod 10 is c. So if k is large enough, then one of these has to be actually c mod 2010 as well, and these are mod 2010 c as well. So the idea is to just create a large enough sequence of AIs so that they're all the same mod to the power 2010. And how are we going to do this? Now apparently
Uh,
yeah.
I have a question. What if C greater than I?
Yeah, you can do like that's what the idea is. No, you have to choose C as very, very large. No, not C as very, very large. I mean, C is the common value that it is mod 10, mod to the 2 to the 2010. So K is very, very large. Like K is very large. So you don't have to like worry about the shortness of the numbers. So the idea is that since I plus 1 rho till k is just more than 2 to the 2010, so some of this must have to be C mod 2 to the 2010, right? This apparently just covers all the residue class eventually, right?
Okay.
So one of this is C. So let's say that value is just J. Then AJ is also C mod 2 to the 2010 and J is also C mod 2 to the 2010. So you indeed have that AJ is equal to J mod 2 to the 2010 that you want. Now we will be just doing something with this. So,
All this stuff about Dirichlet convolution works mod n also, right?
what?
All of this stuff about Dirichlet convolution works mod n as well, right?
I don't know. I mean, what are you saying?
I'm
Like
just
which?
saying all this stuff about Dirichlet convolutions will work mod n as well, right?
Yeah, that will work modern as well. Sure, this will work modern as well. So the idea is you want to generate a infinitely large sequence of AI, which are all the same mod 2010, 2 to the 2010. So indeed, all of these AIs being 2 to the 2010, so the same mod to the 2010, which is a common value, is equivalent to all the BIs. So BI plus 1 till BK, all these BK are 0 mod 2 to the 2010. So you just essentially want to find a very, very large sequence of BI to BK, which says that all BIs are just 0 mod 2 to 2010 and you are just done then. So after to construct such a large sequence, we'll just use something. So we'll just expand this. So B, BD, mu D, mu N by D and D divides then minus 1. So after this, we would like to have what do you say? B of n to be divisible by 2 to the some large power because that's essentially what you want. So you want 2 to the large power dividing Bn. That's interesting. So if you try to write down our first few terms, uh, wait, what?
Huh?
So now the remaining idea is that you have this extra coefficient of 2 and you want 2 to the 2010 to divide BIs. So apparently this must be useful in some way. So if you could have that all BDs that you have here, they are divisible by 2 to the power like say I minus 1. then you will have this thingy divisible by 2 to the I. And this is indeed the main idea. And over here you have Mobius of n, right? So you can just choose n to be a square, non-square free number, and just you can get this made to be 0. So then you don't have to worry about this, and you'll get b divisible by 2 to the I. So this just motivates the inducting idea. So what we'll now prove is that suppose there is a prime p, and if p to the k divides n for some k in positive integer, then 2 to the k plus 1 divides p of n. So I'll just leave the details to the reader. Like this is trivial induction. You can just induct. Okay.
So do you mean 2 to the k minus 1?
It will give 2 to the k minus 1. Oh yeah, it will give 2 to the k minus 1 minus. Yeah. True. So you'll get this by induction. So basically I just spoiled the main idea of this. So basically, if you have like BDs are divisible by 2 to the k, then twice of this will just divisible by just like one more power of 2, and mu of this thing will just become 0 because like n is eventually divisible by p to the k and p to the, which makes n as a non-square free. So you'll just get this thingy. This is follows by induction. And do you just anyone sees the finish now?
Now you just take that all the primes to the power 2011 are co-primes, so you're done.
Yes. So in particular with this, what you have to guarantee, you can guarantee is that p to the 2012 11 divides n just guarantees to the 2010 divides pn. Now this is very interesting. So if I choose say n to be some 0 mod p to the 2011 minus 1 mod let's p1, I will just write p2 to the 2011, and since they're infinite primes I'll just don't care and I'll keep on choosing, and minus 2 to the say p3 to 2011 and so on. So I will essentially get that all n plus 1, n plus 2, they are all divisible by 2011 powers of some prime. And so for all n plus 1, n plus 2, dot, 2 to the power 2010 divides b of I. So apparently generated a large sequence of bi's, which are all 0 mod 2 to the 2010. So you generated a large sequence of ai, which are all the same to 2 to the 2010, and you apparently got this, and you're done. So that's it for the day. Any
Can you
questions?
repeat the part after we got like how we wanted Bn to be 0 mod to the 2010?
Okay, so you understood that we just want to generate a wait, let me just write.
Yeah, I got this part. What you're showing right now.
Yeah, so bi to bk, you want a large thingy which is same to the 2010.
Yeah.
So now I claim a lemma. So if there exists a prime p such that p to the k divides n, then
Yeah.
2 to the k minus 1 divides bn.
Oh, okay.
And this is the, you can just check this by induction. Because the induction, what motivates the induction is that you have an extra 2 here. So if you have some 2 to the power something here, then just 2 multiply will get to the power something plus 1 here. And so you'll just get a larger power of 2 dividing p of n. Right.
Won't the Mobius change that?
So do you see that p to the k divides n?
Oh, okay.
So that like if k is greater than 1, then this just becomes 0. So this just apparently does nothing.
Okay. Wait, and why like p? Why not just do 2 directly?
Why p? What did you say?
Like, why are we using some different prime instead of using 2?
Sure, you like this just holds for all primes, right? We are just this just holds for all prime. You can just say 2 to the k divided and implies this. You can just say for p equal 3 as well. You can choose any
Okay.
prime. We just want to prove a more general result because like that will just help us generate the sequence.
So we want to find like a large sequence where everything has high VP for some one prime.
No, not some one prime, like all could
Like
have
yeah,
different
like
primes.
yeah,
Acha, you get it. Okay.
there is like at least one prime with high VP.
Yeah, exactly. So you can just do that by CRT. So you just do some I which is 0 mod P1 to the 2011 minus 1 mod P to the 2011 and so on, like whatever our sequence is.
Okay, all right.
And I plus 1, I plus 2 is just the sequence for which all BIs are just divisible at 2000, 2 to the power 2010 and you're done.
All right.
So for the source of this, I think it's USA TST. 2010, yeah, P5. So that's it for the day. And you can try this problem. I would recommend trying this one. This has a similar idea to this, though this has some new ideas as well. So this is also a hard problem, like this USATST one. So you can try this one as well. Just take the screenshot of this. Turkey National Mathematical Olympiad P3 and this one also. And try this as a turn over dress cock and it's just like China TST.
Wait,
Yeah,
previous the Turkey National Mathematical
yeah,
Olympiad. Which one?
yes.
One? Oh, okay. Oh, but it's problem 3, right?
Yeah. Let me just stop the recording now. Wait, how do I stop the recording? I have no clue. How? Okay.
On the USA